Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Chapang Mapotani. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. Now, grade 12, in today's lesson, we are focusing on probability, and the topic for this lesson is probability and counting principles. That is, we are now going to discuss counting principles in detail. Right. Now, by the end of this lesson, we must be able to work with probability, counting, and counting principle. And we should be able to do the following. We should be able to apply the counting principle to solve the fundamentals of the counting principle to solve problems using the techniques of fundamental counting principles to solve probabilities where events are not necessarily independent. That is to say, we just want to utilize the fundamentals of counting principles to solve the probability problems, more especially where events are not necessarily independent. Right. This information comes from our TechCrep document and our grade 12 ATP 2024. Right. Now, this is what we have covered last year. Now, coming to this lesson, you are supposed to remember and know the following. Number one, you must remember, you must be able to identify the dependent and independent events. And when we are doing that, we're saying we have to be able to use the product rule for independent events. So when events are independent, we are saying the product rule applies where the probability of event A and event B occurring is equals to the probability of event A multiplied by the probability of event B. Now, we are proceeding to say we have to remember how to use the tree diagrams for the probability of consecutive or simultaneous events which are not necessarily independent. So that is to say, we're going to use the tree diagrams for consecutive or simultaneous events. Remember, the tree diagrams will tell us the simultaneous events or events that are taking place at the same time, right? And which of those events are not necessarily independent. We must be able to solve using them two-way contingency tables for the data involving two aspects. Remember, this is grade 11. We must remember how the two-way contingency tables work. Remember, this one, they give us the relationship between two variables. So that is to say, one variable is on the, let's say, it's going across and the other one will go down. So this is where we can see the relationship between two variables. Now, in most cases, the contingency tables are there to assist us to indicate whether the events are independent or not. Right. Now, our grade 12s. Now, this is our baseline activity, which is based on the grade 11 probability. Now, you will be given 10 minutes to complete this activity. Right. Welcome back, grade 11s. Now, let us discuss the solutions to this activity. So, we are told the following. Number one, we are told that two events A and B such that the probability of node A is equal to 0.45 and the probability of B is equal to 0.3. Probability of A or B is 0.65. Are the two events independent? Justify your answer. Now, let us discuss the solutions to the first activity. So the first activity, we are told that two events A and B such that we are given the probability of node A, we are given the probability of A or B occurring. Are the events independent? Justify your answer. Remember, for A events to be independent, so what are we supposed to do? We are supposed to say, we are saying in this case, the product rule must hold. So this is to say, if events are independent, that is to say, if event A and event B are independent, that is to say, the probability of event A and B occurring simultaneously is equal to the probability of event A occurring multiplied by the probability of event B occurring. That is to say, the probability of A and B occurring, let's say, probability of A and B occurring is 3/10. For these events to be independent, that means when I multiply the probability of event A occurring individually and the probability of event B occurring individually, the answers must be the same. So that is to say, when I multiply A, probability of A and the probability of B, so it must be equal to both events occurring at the same time. So that is how we know that these events are independent or not. Now, let's proceed. Now, we need to start by the following. Okay, let us check what we have on our data. We are told that the probability of node A occurring is 0.45. But remember, for us to be able to know if events are independent, so we must know what is the probability of A and B. So we start by finding the probability of A and B. And already we have probability of A, B. Then we need probability of B. We have that. We need to find probability of A and B. Now, so to find probability of A and B, we'll use what? We'll use the addition rule. However, before we can do that, we must find the probability of A. We have the probability of B. So B is given as 0.3. We need to find the probability of what? Of A. And we are told the probability of node A. So how do we find the probability of A in this case? This is our complementary events. So we are given a complement of A. So we must find A. So we're saying the complement of A is equal to 1 minus the probability of A. So we have the complement of A. This is given for us. We substitute it is 0.45. So probability of node A occurring, as it is given, it is 0.45. It's equal to 1 minus probability of A occurring. So we are looking for probability of A occurring in this case. Now, when you proceed, what do we now have? We solve for probability of A there. We find that probability of A is 0.45. So we have this 55. We now have 0.55 as the probability of A occurring. Now, remember now, we have now found the probability of A. So what else do we need? We need the probability of A and B, which is what we're actually doing in this case. So we're trying to find probability of A or and B. And we're given A or B. So we are given A, probability of A or B. It is given to us as 0.0685. So we are given that probability. So what are we supposed to do now? We can see with this string, we can now use the addition rule to find the probability of A and B. So we can say our product rule reads as follows. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So we are looking for the probability of A and B. So what do we get? We have probability of B. We have probability of A using the complementary rule. We have A or B as it is given. Then we can easily find probability of A. Now we substitute. Probability of A or B, it was given to us as 0.685 as from the data there. The probability of A, we are given that as, we found that from the complementary, which is 0.55. The probability of B was given to us as 0.3 minus the probability of A and B. Thereafter, we just solve the probability of A and B as 0.6185. Now, remember, we found A, we found B, we have A and B, now we found A and B. Now, let us check if these two events are independent. Now, how do we check? We start by checking the left, what is this side? Is our right-hand side. So this is my right-hand side. Now, when I check the right-hand side to say probability of A, which is 0.55, multiplied by the probability of B, which is 0.3. So what we have in that case, we now have probability of A multiplied by the probability of B is equal to, let's just erase them. So the probability of A and the probability of multiplied by the probability of B, it gives us 0, we have the 0,165. Right. Now, as we are proceeding in this case, we are now saying what is the probability of A and B. Remember, we already have found the probability of what? Of A multiplied by the probability of B. Now, if we can check the probability of A and B, it's equal to 0,165. And we find that the probability of A multiplied by the probability of B is equal to 0,165. So we can see that both probabilities are the same. So there we have both probabilities as being the same. Right. So now we say in this case, the two events are independent. Now, let us move on. Now, number 2, we are told that 12 learners watch netball, rugby and athletics. 25 learners watch rugby and athletics. 22 learners watch netball and athletics. 38 learners watch rugby. 5 learners watch only netball and only netball and rugby. And 5 learners only watch netball only. 4 learners athletics only. Determine the values of A, B, and C. So A is that one, B, and C. So we're looking for those, or C, D, which is that one. Right. So how do we do this one? Remember, we were given the Venn diagram on this question. So after we've been given the Venn diagram, we're going to work with the intersections. We start with the intersections. Already, our middle intersection was already filled in for us. So we're fine with that one. That one was okay. We're safe. Now we can check the other two intersections. How can I find the value of A? Now, how would you find the value of A? We check. We are told that 12 learners watch netball. So rugby and athletics. The 12 learners is for everything because it says netball, rugby, and athletics. So 12 learners were already plotted for us. They said 25 learners watch rugby and athletics. So 25 learners watch what? Rugby and athletics. Athletics is here, rugby is here. So this intersection alone, this it's only for how much? It is the total must be what? 25. Now we proceed. 22 learners watch netball and athletics. So netball and athletics. So it's only 22 learners watching netball and athletics. So this intersection again, this one is how much? It is 22. What else are we told? And we are told that 38 learners watch rugby. So the whole of this event rugby, it is 38, all of it together. Now, let us calculate. Number A. A, it is found on the intersection between netball and A. That is to say, for that intersection, the total must be 22. So we'll say 22 minus whatever that is on the intersection, or that is part of the intersection. As we can see, what part of the intersection in this case is what? It's the 12 only. So we'll say 22 total for the whole of that intersection minus the 12. 12 also exists within the intersection. That is to say, the 12 is part of the 22 already. So when I take it out, I want to get a value that does not include 12, which is now 10. So 10 is A alone. So you can see 10 is written here to show you that this 10, it does not go along with that 12 in that case. So that is to say, when you add again 10 plus 12, it must give us 22, because the whole intersection between N and A only must give us 22. We proceed. The value of B. Now, how would you find the value of B? We go and check. B exists in the intersection between R and A. So in the intersection between R and A, that means the whole intersection of R and A, the total must be 25. However, I'm looking for B. B, which is what? Which is just R and A alone without the middle intersection. So what am I supposed to do? We are supposed to take out what? The 12. So when you say 25 minus 12, then we get 13. So 13 is for B alone, which does not include the middle intersection, which is 12 for all of them, right? Then we find that B is equal to 13. Now C, how would you find C now? C is found on R alone. So when you look at R alone, just gonna throw R alone. So on R alone, we have 5, we have 12. I'm just gonna show you that with dotted lines then, show you how this was drawn. And we have 13 there. So I tried to show you the intersections using dotted lines. So that's how those intersections look like. So we're looking for this C here. So what you can see that it's for that sphere R. In that case, what are we seeing there? We are seeing that R is made up of 5, 12, and 13. That is to say, when we say 38 learners watch rugby, so on these 38 learners, we must know that the 38 learners include 5, 12, and 13. But what are we looking for? We are looking for C. So C, it is the one that doesn't include all of those values. So the total for R is how much? Is 38. Because we're told that 38 learners watch rugby. So what do we now do? We can say now the total for that sphere, we remember, we minus the intersections. So this is to say, we minus what? The intersections. So it's 38 minus the first intersection of 5, second intersection 12, third intersection 18. So we minus all of the intersections to get rugby alone. So to get rugby alone, we take out all of the other intersections where the rugby and something else. Then we end up having C. Our C in this case is 8. So that means the rugby only will be 8 in that case. Look at D. Now, we are looking for D. So D is what? D is outside. It means a certain number of learners who are not participating in any of those three sports, rugby, netball, and athletics. So how many learners we have in total? We had 75 learners. Now, not all of them that are not participating. We subtract every event that is shown on the Venn diagram. We'll subtract the 9, minus 5, minus 12, minus 10, which is A there, minus 4, which is A alone, minus 13, which is what? Which is the intersection of B, minus 8, then we get the answer as 14. So D is 14. So to find D of which is not any of them, what do? We take the total and minus every value that is inside of our events. So that's how we find D. So total minus all of those values that are inside of events and all of those in the events. Let's move on. Right. Now we are still doing number 2. Let's look at number 2B now. So on number 2B, it says, calculate the probability that a learner selected at random watches athletics or both netball and rugby. So two things then. So it's either the learner selected watches athletics alone or the learner watches both of netball and rugby. So how do we do this one? We now need to find the probability of the learner watching athletics. Where is athletics? Our athletics is this one. They didn't say athletics only, just said athletics. So whether you watch athletics with rugby or what's or not, doesn't matter. So that means we are talking about the probability of any event in A. So the probability of any event in A, that is to say, when you say athletics, like I said, it doesn't mean athletics only. It can be athletics and netball, athletics and rugby, athletics of an A and all of them. That means whenever there's athletics or athletics is involved, we are looking for that probability. Now we're saying, first one is the 12 over, so everything divided by the total. So it's 12, the middle intersection. So everything that is in sphere A, that is the one that we are looking for on the first one. Plus 13, 13 also is part of sphere A. As we can see that sphere, I've highlighted the sphere for us. Plus 10, 10 also is part of sphere A. Plus 4 over plus 4, which is sphere A alone. Then all divided by 75. So how are we doing this? We are saying, when they say athletics, that means everything in the event athletics. Then we have 39 over 75. Now we're saying or the learner or a learner watches what? Both netball and rugby. So the second one, it's saying netball and rugby. Where's netball? Netball and rugby. So it's only both netball and rugby. So this one it's including excluding what? Athletics, but only what? It's only netball and rugby. So that is to say, we are talking about those who are watching both of them. Not netball alone, not rugby alone, but for both events. So it is the intersection between netball and rugby only, excluding athletics. That's why we are taking only 5. So it's 5 over 75. Thereafter, what do we now do? What we do from here, we add both probabilities. So it's in a probability of athletics alone. Of athletics is 39 over 75 plus the probability of what? The probability of netball and rugby only is what? It's 5 over 75. Or netball and rugby at the same time, actually, because it's the intersection. You can say at the same time. Right. Then what do we now have? Then we have the total as 44 over 75. And our answer is 0.5 and 0.59. So that is our answer. So here, just that disturbing. It was 44 over 75. Now, let us move forward. Right. Now, let us look at the fundamental counting principle, which is our now grade 12 probability. So this is the part of probability that is introduced in grade 12. Remember that we did, it was from grade 11. Now, the fundamental counting principle says, so the fundamental says, if one operation can be done in M ways, in certain M ways, and the second operation can be done in N ways, then the total possible number of different ways in which both operations can be done is M times N. So, to say if you're doing a certain event in a certain way, another event in a certain way, so talking about 2 events here that are done at the same time. So, how can you do the 2 different events at the same time? It's take the first event and multiply with the second event, and that will find the possible ways in which both operations can be done. Right. So we'll focus on pin codes and passwords. So we'll apply these counting principles on pin codes and passwords. We'll talk about arrangements where we have a different or selection. We'll talk about identical item also, and we'll talk about rearrangements. So the fundamental of counting principles to say, if you can do a certain event in a certain way and the other event in a certain way, the probability of or the possible number of ways that both events can be done, it's what? It's it's M ways multiplied by N ways. So it's number of ways you can do the first one multiplied by the number of ways you can do the second one. Now, let us move on. Now, in this case, we're going to look at the trig tree diagram. Let us go back to how we dealt with the trig diagram in grade 11. How do we do it? We just had one branch. We have one branch for the first event, and we are talking about tossing a coin in this case. When you toss a coin, we can either get a head or a tail. So there's 0.5% chance, 0.5 and 0.5 chance of getting a head, 0.5 of getting a tail. In the second event, we can have 0.5 of getting a tail, head again, and 0.5 of getting a tail again, 0.5 of getting a tail, head, and 0.5 of getting a tail. So that's what we say. We are going to have 2 events in this case. So if we say first event, we flip the coin the first time, and when we flip it the second time, these are the outcomes of the second event. So from the tree diagram, what did we do? What we did was we count the total number of outcomes as follows. We just count them to say, okay, for the first one, we can say we have a head and a head. So that is a head, which is what I have there. Then in the second event, it's first event, head. Second one is tail. So the second possible way is head and a tail. So it's head, tail. We proceed again. And if we start by tossing a tail, in this case, we'll say tail and a head for the first event. So it's tail, head. Second event, we had what? A tail and a tail. Then the last event, we have a tail and a tail. So how many ways we have? It's 1, 2, 3, 4. So we had 4 ways that we can do, which is what? Head, 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 tail, tail, head, is tail, head, and tail, tail. So there are 4 outcomes that are possible in this case. Now, what are we going to do now? So using a tree diagram, it can be time consuming. So what we do now, we're going to use what we call counting principles to talk about these events taking place at the same time. So how are we going to do it? So the number of outcomes that we can get from tossing the coin twice. So when you say twice, it's one way, which is the 2 there, and the other way. So we have 2 ways of tossing it. So these are the ways. So we'll use that, just a line to show that 2 ways. So 2 events, first toss and second toss. Then what do we do now? We're saying for the first event, we have 2 outcomes. We have a head on a tail. So it is 2 times. The second one, we have 2 again, it's 1 outcome and 2 outcomes. So it's 1, 2. The first one is 1 and 2. So that's how we do it in that case. So we're saying the number of outcomes will be 2 because there are 2 ways. We toss the coin. The coin how many times? 2 times. So it's 2 times 2, which is how much? Which is 4. If we did it 3 times, it's going to be 2, 1, first toss, 2, second toss, 3, third toss. So that's how we're going to do it in that case. Right. So what we can say now is that using the fundamental counting principles, what are we doing? We are now finding an easier way of finding the number of outcomes for events occurring at the same time. So we can say that as we continue, if you go to event 3, 4, 5, and 6, you'll notice that using a tree diagram is going to be very time consuming. But with counting principles, everything will be easier. Right. Now, let us move on. Now, when you're talking about counting principles, we start with arrangements with repetition. What are they? Arrangements with repetition, we're saying the number of possible ways is equal to n to the power r, where n it is the number of choices that we're having, and r is what? It's number of times you can choose. So number of choices and the number of times. Now let us begin a simple example there to say how many 3 codes. So 3 codes is what? It's a what? It's our r. It is the number of times we can choose. So a 3-letter code. So a 3-letter code, it means 1, 2, 3. So you have 3 events on that one. You can choose made from these letters. Now, number of choices, how many choices do we have? 1, 2, 3, 4, 5, 6. So that's what we have in that case. So we have, how many times can a 3-letter code be formed from the following? So we're going to say in this case, we have how many times? And letters can be repeated. So what are we saying? We have how many letters? 1, 2, 3, 4, 5, 6. So number of letters is how much? 6. Then number of times you can choose, because we are looking for a 3-letter code. So it's 3. So that's why we're saying R, it becomes number of times. We can choose how many times? 1, 2, 3. Then how many choices do we have? 6. So it's 6 choices for the first one. Again, the said letters can be repeated. If maybe, for example, on the first one we take D, then we have 6 of them, then the said letters can be repeated, meaning even on the second choice, or in the second time, what can we do now? On the second choice, we can say we still have 6 choices, because the letters can be repeated. We are replacing the letter. That means if you pick letter D on the first event, you will retain it. Then we'll talk about it again. We'll have D again in the second event. Then we'll still have all those letters in the third event. So this means on the first one, how many options do I have? 6. It's D, G, H, M, R. That is what we're saying. Because we are repeating the letters, that means in the second choice, we still have D, G, H, M, R. On the third one again, we still have D, G, H, M, R. So that's what we are saying in that case. So we can see that letters can be repeated. If letters can be repeated, let's just think about that situation where letters are not repeated. When letters are not repeated, we have 3 ways again, but we're no longer repeating letters. So what does it mean in this case? For the first one, how many choices are we going to have? We're going to have 6. If I pick D, let's say it's 6, 1, 2, H, M, R. It's 6, 1, 2, 3, 4, 5, 6. Now, if I put D in the first one, that means D won't exist for the second one. I'll have how many choices? 5 choices. Then that means I'll have how many? In this case, I will have G, H, M, R. Now let's say the second one I choose R. Then that means for the last event, how many will I have now? GHM. So I will have how many? GHMR. So 1, 2, 3, 4. So here I'll have 4. 1, 2, 3, 4, 5. Oh, there is a letter missing. Oh, T. Letter T is missing for all of them. Remember that? I can see now the letter T. It's not 6. Yeah. So it's 1, 2, 3, 4, 5, 6. Now if I miss one of them, I'm gonna have 1, 2, 3, 4. 5. Then here I'm gonna have 4 in that case. So that's what we are saying there. Then how are we finding the number of ways it can be done? We just multiply all of them. So here it's 6 times 6 times 6, which is just 6 to the power 3. Because the 6 repeating itself 3 times. The answer is not 16. It's a typing error there. So number of ways it's gonna be 6 times 6 times 6 is 36. 36 times 3 times 6 again is 216. So there's a typing error. 2 was missing in that case. Now that is how we're gonna find it. If now letters cannot be repeated, we'll just multiply all of those. Because remember, the fundamental of counting principles is n times m. So that is how all events can occur. So that means we're going to multiply all in that case. So that is how we are working with the counting principles. Now, what we now do, we proceed. Let's talk about permutations. Permutations, we're saying, let's look at arrangements where there is no repetition. What happens when there's no repetition? But remember, we must define a permutation. A permutation is a way of grouping elements in a specific order. So it's grouping of elements in a certain order. Now, what are we doing in this case? When you're working with permutations, when choosing from a different group of multiple objects multiple times and repetition is not allowed, it means we choose from the number of each object we choose from is reduced by 1 in each time the selection is made. Which is the previous example I did. Remember, previous example I had 3 spaces, 1, 2, 3. I said 6, 5, 4. But with permutation, when you talk about the permutation now, we talk about a situation whereby the 6, it will reduce until 1. Then we're going to talk about that in detail, which is now 6 factorial. So we're going to talk about now that in this case. So we are saying with permutations, we are saying we're choosing from different objects multiple times and repetition is not allowed. That means the number we choose from is reduced from each one by each time we make a selection. Remember, first one we had options of 6. After we choose on the first event, how many options we left with now? We were left with 5. After we choose from that 5 events that are remaining, how many are we left with now? 4. So this is without repetition. If you pick a letter, we can't return that letter. That means the total will decrease. So that's what I'm saying. First one we had 6 faces. We take 1. We remain with 5 for the second one. So for the second event, we have 5 choices. Then for the last event, third event, how many choices we have? 4 choices in that case. Now, we use a factorial notation to calculate which is the calculation involving multiplying numbers when they are reduced by 1 successfully until you get to number 1. So we can only say 6 factorial if we're going to start from 6 and go to 1. If we just say 6, 5, 4, we can't say 6 factorial. Why? Because it must be reduced by 1 until the number 1. So what we had on the previous example is 6 times 5 times 4. We cannot say this is a 6 factorial. Why? Because it does not get to 1. So when does it get to 1? It's 6, 5, 4, 3, 2, 1. So this is 6 factorial. Why? Because it goes straight to 1. So from a bigger number until 1, we can now call it a what? It's 6 factorial in that case. Now, so number of possible ways is equal to a p factorial, which is a factorial notation. That is to say, even p, in that case, it was 6. Now, times on the second event, it is 6 minus 1, it's 5. So which is 6 here, minus 1, which is 5. And on the third event, what are we going to have in that case? Multiply by 4, which is 6 minus 2. So p is our 6 in this case. When you proceed, then we say multiply by 6 minus 3 continuously until we get to 1, until we get to 1. So that's what we are saying under permutations. We use a factorial notation. When do we apply factorial notation? Only if the number of that ways it goes down to what? To 1. If it doesn't go to 1, If it doesn't say 5, 4, 3, 2, 1, then it is not a factorial. Let us look at this one in detail. So we are saying, how many ways can the letters in a ring be arranged without repetition? So in this case, we're saying we have 4 options in that case. So what are we saying? We're going to say 1, 2, 3, 4. Why is it 4? Let's look at the first one. We have E, R, I, and N. So it's 1, 2, 3, 4. So you have 4 options there. So for the first choice, we have a ring as it is. It's 1, I, R, N. So that means for the first one, we can use any of the letters. So it's 4. If I use one letter here, if maybe I use E, for example, then I will remain with what? Rin. So how many now? 3. Now, if I choose another letter here, let's say I use N. That means for the third one, when I come to the third event, I have how many options? 2 options to choose from. Then if maybe I check R, in that case, how many I remain with? I remain with 1 option, which is I only. So that's how a factorial notation works. So if we can see, it is reducing in that case. So it is reducing to show you that we are not repeating the letters. It is without repetition. So it is 4 factorial because it's from 4 until 1. So we can call that 4 factorial. So it's going to be a multiplication of all of those numbers in that case. So it is 4 times 3 times 1. Then we get the answer as 24. Now let us move on. Let us look at a permutation again. Now, where the order of arrangement is important. Now, what is happening in this case? We have R introduced there as a specific choice. So we are told of a certain permutation, and there is a specific choice or a special choice that we need to adhere to. Then that will be our R in that case. Now, let's just look at an example to understand this better. They say there are 7 players in the netball team who hope to be a shooter or a goal attack. How many options are there? How many players do we have? 7. So you have 7 factorial in that case. However, so our N is 7. So N in this case is 7. But we have a special or a specific choice. What is a specific choice? From the 7 we have a specific choice of being a goal, a shooter, or a goal attack. How many of them? 1, 2. So we have 2 special or specific choices that are there. So from the 7, we have 2 specific choices. So 7 total number of choices, and specific choices, how many are there? Who hope to be one? Shooter or a goal attack, which is 2 specific choices. Right. So how many different options are there? We're now saying our N is 7. The total was 7 specials. I'll always call them specials or specific choices. Just prefer to say special. Specific choices, how many? 2 of them. So let's check. A number of possible ways is equal to n factorial over n minus r. When I just say nsj, it's just a sample space there for s. So I just explain the s there. So in this case, we're going to say 7 factorial. So when there is n, I put 7. When there is r, I put 2. Simple as that. So n, which is the total, n factorial over 7 minus 2, which is what? Which is, the answer is what? It's 42. So we can see when we have a specific choice, we will subtract that specific choice from the n on the denominator. Right. Let me just go back there and explain to you what are we doing in this case. When you have 7 factorial there, so we have 7 factorial is 7, 6, 5, 4, 3, 2, 1. All over. Remember, from this 7, we're only looking for these 2, a shooter or a goal attack. We can see we have what? So it is 7 minus 2. So it is 5 factorial actually below there. So it's going to be 5, 4, 3, 2, 1. So you can see that when this cancels out, we are left with those 2 specific choices that we were looking for in that case. Right. Identical items. What is identical items? Identical items, we're talking about the repetition of letters. So maybe in a certain letter, there are maybe in a certain way, there are letters that are repeating themselves. We call them identical items because maybe E and E are repeating, so those letters are identical. So we have n factorial over those identical items. So these are identical items. So where M and P are number of different terms, items are repeated. So these are specific items in that case. Now let's look at the word Vanessa. Now, in how many ways can the word Vanessa be arranged? Now let's check. M and P are identical items. Now, in this case, we can say our M, just make an example. In this case, we can say our M is what? We have two S's, we have two S, and we have an A and an A there. So we can say M is for S, can say M is for S, and if M is for S in this case, how many choices do I have for that? We have two of the S's there. Then we proceed. We can say, for example, our P in this case is for what? It's for A. How many A's do I have? Two A's. So P is equal to 2A. M in this case, it will be how much? It will be 2S. So these are the repeated items. So 2S S is repeating 2 times, and A is also repeating how many times? 2 times. Right. So in this case, we're saying there are 2 A's. We can call this one, and the A's we can call them P, and there are 2 S's. So these S's in this case we can call them what? M. So the 2 letter S's, and in that case, we're now gonna talk on that one. We can say NS in this case is what? It's N factorial. What is N? N is the total number of ways. So I just write N there. How many are they? 1, 2, 3, 4, 5, 6, 7. So N is 7. The repeated one is what? Is 2 and 2. So it's 2A and the 2S in that case. Now, what do we now have in this case? We now have, okay, N is 7, total is 7. The repeated items, maybe this is for, let's say this is for S, and this is for what? For A. So how many S's do we have? 2. So it's going to be 2. And how many letter A do we have? We have how many? 2 again. Maybe if, for example, the letter A was 3, so it's going to be 2 factorial times 3 factorial, just to elaborate further on that one. Then, in that case, the number of ways this can be arranged is going to be 1,260, considering those identical items. Right. Let's move on. Arrangement and set position. Now, number of position times the number of arrangement in each position. So what are we doing in this case? We are talking about a situation whereby we have set positions to say, in the first position, we need to have 5 options, second position, third position in that case. That is to say, they said how many ways can 5 math books, 2 African books, and 3 English books can be arranged if they are grouped in their subjects. So these are what we call grouped items. So under grouped items, what are we having? So under grouped items, we have a situation where we say, okay, if math books are grouped, that means they will have their own slot. Then this is for math only. Then the second one, let's say Africans, second one is going to be for Africans, third slot is going to be for English. So these are grouped items. So each and every of these books have their own slot. So in this case, what are we going to do? We're going to say for the slot of M, math is 5. For the slot of Africans is 2. For the slot of English is 3. But how many books do you have for maths? It's 5. So it's 5 factorial. So in this slot, actually, if you think about it to make it more complex, let's hope you're not getting confused with this. In this slot alone of M, it's how many choices? 5, 4, 3, 2, 1. So this slot is made up of 5 options in that one. The slot number 2 is 2 Africans books. So it's 2, 1. So it's 2 Africans books. So you can see that this, it's more like a slot that can be, if you zoom into it, it can be broken down into a factorial to say there are 5 options of putting the math books. There's 2 options of putting African books. Now in those options, we still have another permutation in that case. Then English books, there are 3. So on these 3 English books, so these 3 English books can be arranged in how many ways? 3 factorial ways, meaning it's 3, it's 2, it's 1. So that's what we're having in that case. We'll have 3, 2, 1 in that slot alone. In that slot alone and in that slot alone. So that's why it's going to be factorial, factorial, and factorial, because we have 5 options to put the math books grouped together. Now let us proceed. However, another thing, we'll multiply again by 3 factorial. Why 3 factorial again? It is because these books, this group, it can be pushed in any position. It can be at the first position, the very same group can be in the second position or third position. That means we still have another way that these 3 groups can be arranged. So it's how much? It's 3 factorial. That means it's possible that the maths group can be at the end, the English group can be at the beginning, or the maths can be in the middle, English maybe it's at the first, Afrikaans is at the last. So we're saying, we talk about each group being arranged in its respective places. Then in those groups, we can move the whole group to say, we start with the Afrikaans group, we come to the maths, we go to the English, or we can start with the English group, we go to the Afrikaans, we go to the maths. So it doesn't matter. We say now, these groups individually being arranged within their own set positions, multiplied by what? Multiplied by the number of ways in which those positions can also be arranged. So you can arrange the positions as they are in that case. Now, let us now look at the breakdown of this. Now, in the breakdown, we're saying we have number of positions are 3. So 3 positions, it's maths, Afrikaans, and English. Then you proceed to say, okay, number of arrangements for math books is 5 factorial. Why? As I've explained earlier on, to say on the group or on the slot of math, we have 5 books that used to be arranged for math in that case. So in that case, we say those 5 books also can be arranged in any way in that spot. Then we have arrangements for Afrikaans, we have arrangements for English groups. So that's what we're saying. We're saying for maths, you can say in this math, these books will still be arranged in any way. We have platinum, we have solution for all, we have Shabula, we name all of those math books that we have, answer series and everything. So they can be arranged in any ways, right? Then under Afrikaans, it's a slot again. But in this African slot, we can arrange these books in 2 ways. That's 2 factorial. English, on the slot of English or in the slot for English, we can still arrange these English books in 3 ways. Right. Then we're saying this is what we have. Those are our books there in groups. And we're saying even these groups are on their own. The groups can be positioned in 3 different ways. We can start with the first group of math, or we can start with the English group, or we can start with the African group in all of those arrangements. So we have 5, and this the 3 permutation is 3, 2, 1. So this is where that 3 factorial comes from. So the number of ways in that case was 4,220. Let us move on. Now, let us look at arrangements with restrictions. What are restrictions to say? We are saying restrictions is to say in a certain position, we are restricting to say we only want this certain event. No any other event can be in that position. So that is a restriction in this case. Now they say, how many ways can letters of the weight equations be arranged if the first letter must be E? Now let's just start by this. Just want to start in a simple way. In how many ways can these letters of the weight equation be arranged? Let's just look at that before we can talk about the restriction. Let us not restrict it. Equation is 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So we have 9 letters for equations 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have all of those 9 letters. So we have 9. If I take a 9, 8, 7, 6, 5, 4, 3, 2, 1. So that is what we have. So remember its equations. Just going to make an example with 1. Equations. So those 9 letters. If I took E, then I'll remain with 8. If I now took Q, I'll remain with 7, continuously like that to go down to 1 in this case. So what are we saying? We are saying we have, without any restriction, it was 9 factorial. But now let's look at this. They're saying restriction is to say the first letter must be E. That means in the first in the first slot or in the first position, in our first slot, we only have one option, which is E. It must be only E in this case. Then the rest will be on the other positions. Then what we say, if we check out E, we remain with how many? We remain with 1, 2, 3, 4, 5, 6, 7, 8. So we'll remain with 8 letters. So we'll say 8. Then any other positions we can put as we want. Can say 8 factorial is 8. Then we'll take after picking after the second event, we're going to have 7. After choosing a letter after that third one, 6, 5, 4, 3, 2, 1 in that case. So we still have 8 factorial here because the 8 is reducing until 1. So we have 8 factorial multiplied by the 1, which is the one option that we're having in that case. So it's 8 factorial multiplied by 1. Right. Then we have our answer as 40,220 ways. They said the first letter must be an E and the last letter must be an S. What are we saying? We are restricting 2 positions. Which position? The first position and the last position. So the only option we have here is E. So it's 1 and this one must be S. Then the rest will be distributed inside. How many? So if we take out first and the last, we remain with 1, 2, 3, 4, 5, 6, 7. So 7, 6, 5, 4, 3, 2, 1. We can see that from the 7, we still go to 1. So this one, it gives us a factorial. Now, we'll have that 7 factorial multiplied by this one, multiplied by that one. Then we have the 7 factorial multiplied by those 2 set positions. So when we have a set position, it will depend. In that set position, how many options do we have? Can have 1 option, can have 2 options, we can have 3 options. In this case, there's only letter S. That means we had only 1 position. We have only 1 letter E, it is 1 position. Then the number of ways can be arranged is 5,040 ways. Now, let's see. They said the first and the last letters must be vowels. Okay. First again. So we have a restriction on the first and the last. How many vowels do we have? We have how many vowels? We have 5 vowels in this case. So we have 1, it's E, first vowel. So let me write it again. E. Equations. Now, let us look at the vowels we have in this letter. Is vowel number 1, vowel number 2, vowel number 3, vowel number 4, and vowel number 5. So we have 5 vowels in total. Now, that is to say, in the first slot, we can have 5 options. We have 5 vowels. But if I pick 1 vowel, that means on the last slot, remember, the vowels only applies to the first 2 slots, right? The first slot, which is the first and the last slots, not the first 2 slots, the first and the last. Now, we have 5 vowels to choose from. So for the first one, we can say we have 5 options. If I take 1 vowel, we remain with 4 vowels, and that other vowel can be what on the last event. That means for the last letter, it must be, we have 4 options after we take 1 vowel then the rest will be rearranged again in that case. Now what we're saying, we now remain with 7 again. So if the same, let's say for the first one we took the vowel of A. So vowel A is here, then the last one we took vowel O. Vowel O is there, then the rest is how many remains now? It's 1, 2, 3, 4, 5, 6, 7. So we still have 7 options. Then we have the 7 there, continuing to 1. So we have 7 factorial. We have how many choices here? 5. So it's 5 for the first and 4 for the last. So we just multiply everything by each other. Then that's where we get the restrictions with the positions. Now, let us look at this example. Now, example says 5 learners, 3 boys and 2 girls are to be seated in a row for a photograph. We are saying how many ways can these learners be arranged? Now let's look at the solution. How many learners can they be arranged? How many learners we have? 5. So we have 5 positions. 1, 2, 3, 4, 5. Then we have the 3 boys. How many positions? 5, 4, 3, 2, 1. So we have 5 factorial ways in which they can be arranged. Easy. Second one, how many they can be arranged so that the girls sit together and the boys sit together. So what are we doing here? We are grouping them. We're saying all the girls, 1 boys, 1 position, all the girls, 1 position. But we look at one thing. Here are my boys. Here are the girls. So the boys are how many? 3. The girls are how many? 2. But in these 3 boys, the 3 boys they can sit anyhow. So we have 3 factorial. We have the 2 factorial. And girls also can sit anyhow. So we have 3 factorial to say, maybe this is a bench. In the bench for boys, we can start with boy number 1, Thabo, Sipho, Karabo, for example, making an example. And in those 2, we can also start with Karabo, Sipho, go with Thabo. We can also start with what? We can now start with Sipho, Karabo, Thabo. So that is why it's just 3 factorial in that case to say. We can start with any of the boys in that case. So in this is the bench for the boys. It can be like that. The bench for the girls also, same thing can apply to say it's Lebo and Lerato, not Lerato, just use a different letter. Maybe Lebo and Kopano, for example, in that case. Now we're saying it's 2 ways. We can start with Lebo and Kopano or Kopano and Lebo. So that's why this gives us a 2 factorial to say. In the bench for girls, the girls also can sit either way. However, we can also say the following. We can start with any bench. We can start with the bench for boys and the bench for girls. Now, in this case, we can start with the bench for boys, or sometimes we can start with the bench for girls. We still have 2 ways of doing this. We still have another 2 factorial in that case to say both benches can be put either way. So, if a bench for boys, we have a bench for girls. Then what we're saying is that even the whole bench of girls, which is 2 girls that are there, we can start with the 2 girls and end with the 3 boys. So we have 3 boys, 2 girls, and we also have 2 factorial. So we can start with any of the bench. So it's 3 times 2 times the 2 factorial of arranging the bench. Then the answer is 24 ways. Now, grade 12, I will give you 5 minutes to complete this activity. Right, welcome back, grade 12. Now, let us look at the solution, or let us discuss the solutions to this activity. So we are told that there are 7 different shirts, 4 different pairs, and 4 different pairs of trousers in a cupboard. The clothes have to be hung on a rack. In how many ways, different ways can the clothes be arranged? Now, let us look at the solutions to this. Now, let's look at number 1. A. So we are saying, how many trousers do we have? We have 7 different shirts plus 4. So how many do we have? We have 11. So you can have 7 spaces. 1, 2, 3, 4, 5, 6, 7. So it's for trousers. 1, 2, 3, 4. It's 4. It's for 7 shirts. And it's for the trousers in that case. So we can say that this one, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So N, it's going to be 11. Then what are we saying in this case? We are now saying, because it's 11 going back to 1. So it's 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 3. 6, 5, 4, 3, 2, 1. There we go. So we can see that if we hang a certain shape, we can't hang it again on the second part. So we've hanged it. We cannot repeat hanging it. That's why there's no repetition here, because it's just a shade. You cannot repeat the shade again because you are putting them on a rack. Now that's what we're saying. It's n equals to 11, so it's just going to be n factorial, which is n 11 factorial. Then we get our answer as 39,216, 916,800. Number B. In how many ways can the clothes be arranged if all shirts are to be hung next to each other and all pairs of trousers are to be hung next to each other on a tray? Easy. Saying shirts next to each other, shirts alone, and trousers alone. We can talk about those benches again. It is the benches for what? For shirt. This is a benches for what? For trousers. Now, how many shirts do we have? 7. So in these 7 shirts, it's a factorial again, because we can start with any shirt and we are putting all of this shirt in one place or together. So when we say together, we can think of a bench to say all of the shirts will be here, the pink one, yellow one, green one, all of those things. We can start with the pink one, we can start with the gray one, doesn't matter. Now, we are proceeding to say, and the pairs of trousers to be hung next to each other on a rack. Now the shirts, how many are they? It's 4 of them. Now in the 4 trousers, what are we saying? These 4 trousers, what can we do? In the 4 trousers, we can start with any trouser. We can start with the pink trouser, or the rest time we can start with the yellow trouser and everything in that case. However, both groups again, we can start with the group for shirts, or we can start with the group for what? For trousers. That means we still have another 2 factorial. So we'll have 7 factorial times 4 factorial times the 2 factorial. Then we get 149,920. Now, so that's all we have for the first activity. Now, let us deal with the second part of counting principles. Now, in the first part, we only the counting. Now, let's talk about the probability within counting principles. Remember? Now, probability, we're saying, in a counting problem, we are required to calculate the probability that an outcome will satisfy a certain condition or restriction. Remember, counting principle, we just had number of ways of arranging something. Now, here we're talking about satisfying a certain restriction to say, what is the probability of starting with the pink shirt? Just making from the last activity we had in that lesson. So the probability is saying it is given by a number of possible ways of meeting a condition over a total number of possibilities. Now let's say, for example, we have 7 children, 7 or let's just say 7 shirts which are in different colors, blue, green, yellow. So let's say it's 7 factorial in that case. Then we're saying, what is the probability of selecting a yellow shade? And there's only one yellow shade. It's going to be 1 over 7 factorial. So that's what we're dealing with in this case. So the probability of an event is equal to the probability of an event, which is a certain condition that we are satisfying. When I said probability of picking up a yellow shade, which is just 1 in that case, over the total number of probabilities. Now let us look at probability using counting principles. Now let's look at this example. Now in this example, we are told that a new series of vehicle registration consists of 2 alphabet numbers, excluding what? Excluding vowels, and the letter Q, followed by the 3 numeric digits, 0 to 9, followed by 2 alphabet letters. How many such numbers are possible if repetition of letters and or digits is allowed? No repetition. The last one is what is the probability. Now let us go to this one. Now we are told that a new series of vehicle registration consists of 2 alphabet letters. So it's 2. Okay, let me just do it here. 2, 1, 2. So these are alphabets. Just gonna say A. Then followed by 3 numeric digits, 1, 2, 3. So these are numbers. And followed by the 2 alphabet letters. We have 2 alphabets in that case, where repetitions are allowed. So this is alphabet. So it's a group for alphabet, group for numbers, group for alphabet again. So what are we saying? We're saying it consists of alphabet letters excluding vowels. How many vowels do we have? We have 5 vowels. Okay, we have 26 total letters. How many vowels? We're excluding 5 vowels. And the letter Q minus 1 again, which is letter Q. Then we have how much? 25 choices. Not 25, 20. It's 20. Now, how many ways can you say? So for alphabet, we have 20. So we have 20. And they said the repetition is allowed. So it's 20. For the second option, we have 20 again. For the last alphabet, you still have 20 because repetition is allowed. Even if you choose T here, we can still have T again. It can be TT again, for example, then. Now, also, we go to numbers. The numeric digits 0 to 9. And we are saying, even numbers, we are repeating this one. So 0 to 9. So 0 to 9, how many numbers do we have? 0 to 9, it's 10. So we still have 10. Repetition is allowed. If I choose 1, I still have an option of choosing 1 again in the second slot. So we still have 10, we still have 10. So that is our counting principle. We just multiply everything in that case. So we're saying, oh, I've done it there. For the first one, it's for our alphabets, 20 times 20. Second group, it's our numbers. How many numbers? 1, 2, 3. So we have 3 numerics digits. So we have the 3 there. Then we say 1, 2, 3. It's numbers. Then 2 alphabets again, which is 20 and 20. Because repetition is allowed. Very important. When you see such questions, guys, what you're supposed to do is 2 alphabet letters. We know that there's 2 slots. You indicate that nicely. 2 alphabet letters again. So you underline this as you read questions. Then those are number of possible ways it can be done. Now, let's look at number B, where repetition is not allowed. Very interesting. Let's talk about this one. So remember, for our alphabet, we have how many? 2. Numbers, we have 1, 2, 3. Alphabets, we have 1, 2. Remember, for our alphabet, it's 20. For our numbers, it's how much? Our numbers is 10. So these are numbers, alphabets. What we have? First time, when you choose it, we have 20 options. Repetition is not allowed. If you choose any letter, that means it's 20 minus 1 for the second event. So if you choose A, you can have A again on the second one. So you'll have 19. Let's go back to letters. Let's finish with the letters first. Then, after you choose maybe T, we can have T again. We go back and say, okay, we have, in this case, we'll now remain with how much? 18. After you choose here. After you choose from this 18, how much we have now? We have 17. Done with the letters. Let's come to numbers. We are not repeating digits also. That means first time with the number, we choose, we have 10 choices. Second time, after you pick maybe 0, for example, second time you'll have how much? 9. Third time we'll have how many choices? 8. So that's what's going to happen in that case. Right, now let's look at this. So we're saying 20 and 19. So that's what we have there. We have 20 choices. After you pick the first letter, we remain with 19. Go to letters again. After you have 19, choose again, we have 18. After you choose from the 18, we remain with 17. Numbers 10, 9, 8. So we just multiply everything together. We have 83,721,600. Number C. Now let's look at this one. What is the probability of the card number plate to start with T if repetition is not allowed? We start with the total. Probability of an event, it's equals to probability of a certain event that we're satisfying over probability of S, which is the total for this case. So we need to find the total first. What is the total? When you say repetition is not allowed, the total is that one of repetition not allowed over starting with T. That means we are doing what? We are restricting to say here we are starting with T and repetition is not allowed. When you start with T, that means first lot only have an option of 1, which is T. Then from the 20, we've taken out T, we remain with 19. Then after we take from the second option, or position, we remain with 18. After we take from the 18, we remain with 17. Thereafter, numbers are still the same. They are just not repeated. Then we're going to say probability of T is what? Probability of meeting a certain condition, which is that of starting with T, over the total of the not repeated one. Then is 1 over 20, which is 0,05. And now, Petros, you are given 10 minutes to complete this activity. Right, welcome back, graduates. Now, let us discuss the solutions to this activity. So, we are told that in Gauteng, the number plates are designed with 3 alphabetical letters, excluding 5 vowels, next to one another, and then 3 digits. So, let's just read the question. We have 3 alphabetical letters, excluding 5 vowels. So, this is what I'm excluding. Again, next to each other, 3 digits. So we have alphabet, we have numbers, which is digits, 0 to 9 next to one another. No restriction there, right? The GP is constant for all of them. Number plate. So example, it's going to be letters and 0, 1, 2, and this is going to be constant. It will always be like that. Digits and letters may be repeated in the number plate. Let us see the first question. How many unique possible number plates are available? Let's check this one. So what we do in this case is that we have 3 for letters. So we have 1, 2, 3 numbers. It's how many? 1, 2, 3 again. So this is our alphabet. I'll just say A. These are our numbers. And this is our GP. It's always like that. So GP, these are state positions. because always gonna be G and P. It won't be a PG. For example, it's always G and P. So this set position will always be 1 times 1. So how many options do we have? We have alphabets. It's excluding 5 vowels. We have 26 minus 5, which is how much? 21. Right. Then numbers. How many numbers we have? 0 to 9 is 10 numbers. So we have 3 spaces for numbers. We have 3 spaces for alphabets. Now, how many options do we have? The third digit might be repeated in the number plate. So we can now have 21. When we can repeat them, if I check T, I'm going to replace T again. So it is with replacement. I'll have 21. I'll have 21. Again, even digits can be repeated. It's 10. Still have 10 digit numbers. Again, if I take 1, I'm going to put back 1 again and make a second trace. So that means I'll have 10 again. Even if I take 2 on the second trace, I'll replace the 10, the 2 again. I will have the 10 in that case. So 21, 21, 21. So I pick a T, I'll replace it again. T with replacement and with repetition. So that's what you have. These are our alphabets. These are our numbers. This is our GP. So GP is a set position in that case. So we have 9,261,000 in that case. Right, let's move on. How many unique number plates are available if letters and numbers are not repeated? Let's go to this one, the nice one. So we are told that how many positions do we have? Remember, 1, 2, 3, 4 numbers. 1, 2, 3, 4. So 1, 2, 3, 4 alphabets. 1, 2, 3, 4 numbers. GP. GP is 1 and 1. Set positions because always GP in that case. Right, we're proceeding now. We have 21 on the first trace. I take 1. I'm not replacing. That means I will have 20 for the second one. I take 1 again. I'll have how much? 19 for the third option. I'll have 19 there. Numbers not repeated. I have 10 numbers initially. When I take 1 number, I remain with 9. When I take another number, I remain with 8. So that's what we're going to have. That in that case, we have 20 times 21 times 20 times 19 times 10 times 9 times 8. 1 and 1 is for GP. Then we have 5,745,600 ways. Then let's go to number C. This is nice. What is the probability that a car's number plate will start with Y in this case? Remember, we are now looking at C, and C we are still continuing to say numbers can be repeated. So we have the total, because probability, remember, it's P of an event. It's always over P of a sample space, P of an event. So it's always over the total. Total is the one of repeated. If not repeated, we're going to use the other total now. So the total of repeated is this one. We had on number A, which is 21 times 21 times 21 times 10, 10, 10, 1, 1. Right, start with Y. What are we saying? We are restricting the first position to say in the first position, we're going to start with Y. So only one option we have for the first. Second one, we'll replace the Y again. We'll return the Y in that case because we are with repetition. Then we're going to say 21 again. Whatever I pick, I will replace it back. I still have 21 numbers. Nothing was altered. Then we have 441,000. Then we can say probability of Y occurring. So Y, it is a condition of meeting Y. To start with Y, that special condition is 441,000 over our total is 9,261,000, which is 1 over 21, which is 0,048. Now, let's look at number D. Number D, it says, what is the probability that a car's number plate will only contain 17? Interesting in this one, like this one. Right, remember, start with the total. Letters can be repeated. Select the total there. Number 2, the alphabets are not affected. Then we look at this one. Here we are saying start with only 17. So in this case, 17, we're saying this is the 17 there. Just going to show you with the right there. To show you that it's the restriction to say if I start with 7 here, then I have 9 choices. That means if I take 7, I'm going to replace it. I will remain with 9 and 9. Now for the second one, whatever I choose, I'm going to replace again, but 7 is no longer there. Then for the third one, I do the same. Plus another situation whereby if I have maybe 3 7, so 7 is in the second position. Remember now, this is 7, this is my 7, this is my 7. So we're talking about 7 in different positions. Where we're saying will contain only 7. So we are restricting 7. When we're saying restriction on when we're saying one number, that means in that position it will be 1. So we're saying when 7 is in the middle, then we have the other numbers that are covering it. Plus another way to say we are ending with 7, but we have 7. That means just to say 9 and 9. So we're saying only 7. That means 7, there's only 7 here. That's why we remain with 9 options here. Then we can have 7 in the middle. So that's what we're having. So that is the special event that we are satisfying over the total. Then we have 0,243. Now, our grade 12s, you are given 10 minutes to complete this activity. Right, welcome back, grade 12s. Now let us discuss the solutions to this activity number 3. Now let us look at this one. We are told that consider the word Johannesburg. The repeating letters are regarded as identical. Very important. And how many different arrangements of the letters with this word are possible? If letters of this word are arranged randomly, what is the probability that the resulting word will start with G and end with J and end with G? Now, let us look at number 1. So number 1 is saying how many possible arrangements are there in this letter. Remember, this one is the one of identical items. We're going to say a number of possible ways. It's equals to n ways over m times, I'm just going to say p, n in that case. So these are the repeated letters. Now let's check how many repeated the letters we have. This is Johannesburg. We have a double N then. And we can check n is the only letter that's repeating. So we only have one letter repeating. You can say our M is 2. We have 2 N's. 2 N's. So that means we have, how many letters we have in Johannesburg? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to be 12 factorial, which is the total over. There's only one repetition of N, which is over 2 factorial. Simple as that. So there are 2 N's. So you can say number of events, we're saying it's N over P in the factorial. In that case, it's 12 over the 2 N's that are repeating. Number B, what is the probability that all these numbers are arranged in the resulting word start with J and end with G? Now, what is happening? The total probability we have is 12 factorial. Remember that our total is 12. We're talking about the probability here. Now, how many ways this can this be arranged? Let's check. Johannesburg. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So Johannesburg, it's 12 factorial. We are saying they start with J. So the first position is restricted to J only. The last one is restricted to what? To G. So the first 2 are restricted. Then the rest of Johannesburg is going to be in the middle. So how many options do I left with? I removed 2. I remain with how many? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We can see that in the middle, we still have the factorial there. So we still have a 10 factorial. We have a 10 factorial multiplied by the first position, multiplied by the last position over 12 factorial, which is what we have in that case. Then is 1 over 32, which is 0,08. Now let us look at this one. Interesting. If certain restrictions were placed in group of digits, an area code must contain 3 digits. The first digit cannot be a 0 or 1. Exchange code must be 3 digits. The first and the second digit cannot be 0 or 1 again. And therefore, it must be a number. The first cannot be 0 or 1. Now, how many ways can this be formed? Area code. First one is 3 digits. It's 1, 2, 3. The second one. So this is the area code. I'm going to say it's A. The second one is how much? Exchange code. 3 digits again. 1, 2, 3. I'm going to call it E. The last one is what? It's a number. So I'm going to say number. How many positions? 4. 1, 2, 3, 4. Don't space them. Now let us look at this one. Area code is saying the first one cannot be 0 or 1. Only the first digit. So only the first digit cannot be 0 or 1. So how many numbers we have? Because the code we have 10. The first one cannot be 0 or 1. So two numbers cannot be on the first one. So we have 8 on the first one. Now, that means the other ones, here we can have all of them. So we can have 10. We can still have 10 because the numbers can be repeated. Now let's come to E, exchange code. On our exchange code, what are we told? We are told the restriction is the first and the second digit cannot be 0 or 1. That is to say, okay, the first or second, it cannot be 0 or 1. 0 or 1 is how many numbers? It's 2. So we have 8 to choose from and 8 to choose from here. Cannot be 0 and 1 in these two positions. And the last one, it can be any number. So it can start or go to 10. The last one, what I was saying, numbers, it must be 4 digits. The first digit must be a 0 or a 1. So on the first one, I only have two options, 0 or 1, nothing else. Then the rest can be any number. So that's what we have to say. Area code, the first digit cannot be 0 or 1. 0 and 1 or 1 is 2 of them. So it's 10 minus 2. Then the rest is going to be 10 and 10. Second option, we are saying, on the second one, we're saying exchange code, the first and the second cannot be 0 or 1. So we can only have 8 options for the area exchange code for the first two slots. So it's 8 and 8. Then the last slot of the exchange code can be 10. We can have that 0 and 1 now. The last one, we are saying the first one must be 0 or 1, which is 2 options only. Then others, 1, 2, 3 slots, they can be the same. So our answer there, we can see, we multiply everything together, we get that answer, which is a period then. Right, let's go. Determine the probability at random that a chosen cell phone digit will be a valid number. How is it going to be a valid number? We're going to start by saying probability of an event is equals to an event. So the event in this case is going to be the one of it being valid over the total outcomes. Probability of S, which is the total. With the total, it doesn't matter whether it's valid or not. But for it to be valid, we apply the what? Apply those restrictions we have. So valid is the restrictions being applicable, and total is just no restriction. So total is everywhere that we can arrange these numbers. So to arrange all of them, it is 10 numbers, it's just 10 to the power 10. So that when we have them, then the valid number, which is the one of applied restriction, as we did in A, it is the one of restrictions. Valid, it means the one of applying restrictions. So valid over the total, even if the total, guys, it can be an invalid, it's fine, it's just total. Then we can have 0,64 over 625, which is 0,101024. Right, great works. Now this is our homework. We'll discuss the solutions to this homework in the next lesson. Right, just copy down the homework. I'll give you 5 minutes to copy down everything. Now, let us look at the summary of the lesson. Summary of the lessons, we're working with counting principles. We talk about arrangement with repetition, where we're saying M is the number of choices, R is the number of times you can choose from. So this is why we just say 10 to the power 10, for example, as we did on the last one. With repetition, numbers and letters can be repeated there. Without repetition, we talk about factorial, and we only apply factorial, remember, if a number goes from maybe 8, it goes straight to 1. If it doesn't get to 1, maybe it's 8 times 7 times 6, it ends there. This is not a factorial. It is a factorial only if this number goes to 1. So it's 8, 7, 6, 5, 4, 3, 2, 1. Then gives us 8 factorial. Let's proceed. We have order, where order of arrangement is important, where we have a special choice or a specific choice, where we say we have the total, over the total. How many specific choices or how many special restrictions do I have? Maybe 2 or 3. Then we talk about those 2 or 3 choices. Or we have a certain another way of doing this, where we have our calculator that we can utilize in that case. That means we're going to have to say shift and find the word NPR on our calculator. Then N is going to be the total is 7, maybe it's 7 specific choices P R. R is going to be made specific choices is 2. Then 7 PR P2, then we get it as the correct answer. Then identical items where P and M were different items that are repeated. Here we're talking about letters that were repeated. Say in any letter that we have, let's say exceed. Put it wrong. Let's say exceed. So in this word of exceed, for example, if I was looking for these identical items, the number of ways we can now say 1, 2, 3, 4, 5, 6. So it's 6 factorial over identical items. How many are they? It's letter E. How many does it repeat itself? 3 times. It's going to be 3 factorial in that case. So this is the repeated letter, which is letter E. How many letter E's do I have? 1, 2, 3. Right. Then we talk about set positions, where we're saying when we set a position to say the first letter must be P, the other letters can be any letter. Then the set position to be what? On position number 1, it will be 1. Then others will have the continuation of or the rest of the letters remaining. Now, let us check. Next lesson, we're going to focus on mathematics paper 1 revision. And thank you, great works. Enjoy the rest of your